Bases. The properties of bases differ from those of acids. The properties of bases are bases, when you dissolve them in water, tend to taste bitter. They have a bitter taste in our mouth. Not that I recommend you tasting bases to find out if they're bitter, but that's what they do if they get in your mouth. Bases also change the color of acid-base indicators. We'll talk more about that later in this chapter. Dilute aqueous solutions of bases feel slippery. So if you take some lye, which is the active ingredient in Drano, and dissolve it in water and dip your fingers in the water, it will feel slippery. The reason why, it's dissolving the protein in your skin. Thus it makes a great drain cleaner because it dissolves hair that might be clogging your drain. Bases also react with acids, just like acids react with base. So bases react with acids and they produce salts. A salt doesn't have to be NaCl, and water. And if we have equal amounts of each, we have a neutralization of that base, and all we'll be left with is salt and water, no acid, no base. Bases also conduct an electric current, and we'll see later it's because they, when dissolved in water, will form ions. And since they form ions, that means that they are also electrolytes. So anything that can conduct electricity because their ions are formed are electrolytes. Now here are some common bases, and when you place the base into water, these are the ions that will be formed when it dissociates, breaks apart into ions. So we have the first one is calcium hydroxide, and it'll break apart into a calcium ion and 2 hydroxide ions. But as you can see, the common theme through all these bases is that they all produce an OH negative, a hydroxide ion. So that's an important thing to remember. Now we want to start going through a process of how we define what an acid is, and this is our first definition, so it will be matched closest with what we've studied so far. And a guy by the name of Arrhenius defined acids and bases are because they produce ions in solution. So an Arrhenius acid was going to be any chemical that when you dissolve it in water increases the concentration of the hydrogen ions. Notice the H plus, hydrogen ions. So acids produce hydrogen ions. If you remember in the formula for an acid, they all begin with H. And an acid will ionize in a solution, and it will increase the number of hydrogen ions that are present. Now an Arrhenius base is a substance that increases the concentration of the hydroxide ions when you dissolve them in water. So the hydroxide ion, the OH negative, is increased in a solution when you dissolve a base in water. So you can see the difference. Arrhenius produces hydrogen ions, Arrhenius acid produces hydrogen ions, and Arrhenius base produces a hydroxide ion. So another thing that's different, acids will ionize in a solution. They're producing ions that weren't there previously, and bases commonly dissociate. Bases already are ionic compounds, and they're just breaking apart to release the hydroxide ions. Acids are molecular compounds, and so they aren't made up of ions, but they do ionize and produce, and the hydrogens that they have in their formula will become an ion. And so their water solutions are known as aqueous acids. That's the way we describe them. So if we're talking about an acid, we usually mean it's aqueous, means it's been dissolved in water. Now, all aqueous acids are electrolytes. That means if I dissolve them in water and they ionize to produce ions, these ions will conduct electricity, and that means they are an electrolyte. So because acid molecules are sufficiently polar, uh, water molecules can attract one or more of their hydrogens and rip it off from the molecule to make the hydrogen ions. And we have learned previously that when hydrogen ions are in an aqueous solution, those hydrogen ions are hydrated to become hydronium ion, the H3O plus. So it's like an H2O attached to an H plus. So this would show the ionization of nitric acid. HNO3 is nitric acid, or hydrogen nitrate technically as a molecule, but once it's ionized in water, it becomes a hydronium ion and a nitrate ion are formed in it, and thus it can the ions allow it to conduct electricity, and so it's an electrolyte. Now, how strong is an acid? Well, the strength of an acid is determined by how completely does that molecule ionize in an aqueous solution. So strong acids completely ionize or very nearly completely ionize in a water solution. So a strong acid then would is also a strong electrolyte. Now that's not necessarily true. Every strong electrolyte is not necessarily a strong acid, because as we'll see that there are other ways to have strong electrolytes besides this. But if it's a strong acid, it's a strong electrolyte. Here are some examples of strong acids. The first one is perchloric acid. Notice it has the ClO4 because chlorate is ClO3, and that would be chloric. And this has one more oxygen than that, and so that's why it's called perchloric acid. And then there's hydrochloric acid and then nitric acid. Those are our examples. So if they ask you in an assignment for some examples of strong acids, use these. In water, we say that 100% of these acid molecules are ionized. We're saying that none of the original molecules are left. They've been completely ionized into just ions. The strength of an acid depends on the polarity of the bond between the hydrogen and the elements that are bonded to it, and the ease with which that bond is broken. So polarity and determines the strength of the acid, and then how easily is that bond broken. So acid strength increases with increasing polarity. So the more polar the molecule, the stronger the acid, and the weaker the bond energy, or the energy that I have to put in to break it apart. That's bond energy. The less that is, the easier it'll form ions. So an acid that releases few hydrogen ions in an aqueous solution is going to be a weak acid. So notice that the strength of the acid is determined by how many hydrogen ions are produced. If it produces few, it's a weak acid. So aqueous solutions of weak acids containing hydrogen ions and the anions, but they also contain some of the original molecules that have not ionized. They're dissolved, but they're not broken apart into ions. Now, each strong acid is assumed to be completely ionized and to give up one hydrogen ion per molecule. We're assuming that to be true when it is a strong acid. And the number of hydrogen ions, though, in the formula does not indicate the acid's strength. So just because we have a formula that has more hydrogens in front of the anion, like for instance, phosphate or phosphoric acid would be an example of one that's not it has 3 hydrogens it could give up, but it doesn't give them up readily. So usually when they have multiple hydrogens, it may ionize the first one easily, and then the next one would be more difficult, and the more they have, the more difficult it gets. Okay, so the fact that phosphoric acid has 3 hydrogens per molecule doesn't mean that it's a strong acid. It still goes back to how polar is the molecule and what's the bond strength. Most bases are ionic compounds, not all of them, but most of them, and they contain a metal ion, elements on the left side of the periodic table that have a plus charge, and a hydroxide ion. We noticed that in that pattern when I showed you that chart, that they all have an OH attached to some metal. Now, because these bases are ionic, they dissociate when dissolved in water. And so if they completely dissociate in it, then we have a strong base. So when a base completely dissociates in water to yield hydroxide ions, the solution is referred to as strongly basic. So here's an example. This is lye, sodium hydroxide. When I dissolve it in water, it forms a sodium ion, and there's my hydroxide ion. That's the part that makes it a base, not the sodium, but the OH is the part that makes it the base. Now, in different solutions, if we start out with just pure water, and we'll talk about this concept a little bit more in the future, but if you have pure water, we consider it a neutral solution. It's not an acid, it's not a base. And what is true in there, water tends to self-ionize to a very small amount, and so it produces some hydrogen ions which are hydrated. So in other words, we have a hydronium ion, and then we also have some hydroxide ions, and they're in equal amounts. So if they're in equal amounts, then we say it's neutral. An acid is one where the hydronium ion, when I put something in solution, it adds to the hydronium ions, and it will be now more than the hydroxide ions, and so we call it an acid or an acidic solution. If we put a base in that neutral water, the base will add to the hydroxide ion concentration, and so then we call it a basic solution. But not all bases are ionic compounds. Most of them are, but not all of them are. Ammonia is an example of a base that actually is a molecule that produces hydroxide ions, not because it ionizes, but because it actually reacts with water. And in the process of reacting with water, the NH3 gains one hydrogen from the water. So imagine the H2O losing one of its H's and attaching onto the NH3, and now I'll have an NH4 ammonium ion, and what was left of that molecule of water is an OH, and there's the OH. So in other words, it's formed because it reacts with water, not because it ionized. So ammonia doesn't ionize, it reacts with water, but it is a base because it produces hydroxide ions. The strength of a base then depends on to what extent the base dissociates, or you could say adds hydrogen ions to the solution. So for example, if I have potassium hydroxide, which is KOH, is considered a strong base because it completely dissociates its ions in an aqueous solution. So this is an ionic compound, and so it's a very strong base. Even if it's dilute, it'll be considered strong. So here is the dissociation of KOH. Notice it produces a potassium ion, but the part that's important in this discussion is the OH negative, produces a hydroxide ion. Strong bases, because they produce ions, are electrolytes. And bases that are not very soluble do not produce a large number of hydroxide ions when they're added to water, and so consequently they're not very strong. They're considered weak bases. So for example, the metal hydroxide like copper hydroxide is not very soluble in water. Only a small amount dissolves in water. So they can't produce a strongly alkaline solution, which is another name for basic. Uh, they can't produce a strong alkaline solution because it doesn't dissolve very well, and thus it doesn't produce very many ions, hydroxide ions. So ammonia is highly soluble though, but it's still a weak electrolyte because the concentration of hydroxide ions in the ammonia solution is still relatively low. So even though it dissolves in the water, it doesn't react a whole lot with the water. So there's not going to be a lot of hydroxide ions formed. So we would consider ammonia a weak base. So if they're asking for examples of a weak base, here's one. If they were asking for examples of a strong base, you'd use the sodium hydroxide that we had a little bit earlier. And that's the end.